So in today's video, we will be looking at the titration of a weak base with a strong acid. So our question is, 50 milliliters of 0.105 molar ammonia is titrated with 0.1 molar HCl. The Kb of ammonia is given to us, which is 1.8 times 10 to the negative 5. So we're going to be looking at four different things. First, we're going to be looking at what is the pH initially in the flask. What is the pH before our equivalence point? What is the pH after our equivalence point? And finally, we'll be analyzing the titration curve of a weak base with a strong acid. So our first question is, what is the initial pH of the solution in the flask? Well, all that's in our flask right now is 0.105 molar ammonia. So all we have to do is calculate the pH of this weak base. So we're going to use our rise table to calculate the pH of this weak base. And for a reaction, we're going to be using a generic reaction so that you could be using this same reaction for any other weak base compound you have. So we'll denote ammonia as B, which is the base, and it's going to react with water to create its conjugate acid, which is BH+, and it'll be making OH-, hence a base. And so BH+ in this situation would be the ammonium ion, which is NH4+. So what is our initial amount of our base? Well, since we're in a flask and the volume is constant at 50 milliliters, we can use the same molarity as our initial amount, which is 0.105 molar. We have zero amount of our conjugate acid or our hydroxide. So what's going to happen in our change? Well, we're going to lose a little bit of our base because it's going to react with the water, and hence we'll lose a little bit of the water, and we would gain it on the other side. So our final equilibrium values would be 0.105 minus X, XBH+, and XOH-. And we don't really have to consider water because it won't be in our equilibrium expression. So moving on, our equilibrium expression for our base is Kb, and that will be equal to BH+ times OH- all over our base. And what are those values? So algebraically, we said it's X multiplied by X for equilibrium values, and the equilibrium value of our base, which is ammonia, would be 0.105 minus X. And this would all be equal to the Kb, and the Kb given to us in the last slide was 1.8 times 10 to the negative 5. Okay, so now let's solve for X. And what will X give us? Well, it will give us the final equilibrium concentration of our hydroxides, so we can get the pOH and finally the pH to figure out what our initial pH of our flask is. So let's use the quadratic formula to solve X. X squared over 0.105 minus X is equal to 1.8 times 10 to the negative 5. We can rearrange this equation to get X squared is equal to 1.89 times 10 to the negative 6 minus 1.8 times 10 to the negative 5x. And we could rearrange this into x squared plus 1.8 times 10 to the negative 5x minus 1.89 times 10 to the negative 6. Set that equal to 0. And if we set up our quadratic formula, x will equal negative 1.8 times 10 to the negative 5 plus or minus the square root of 1.8 times 10 to the negative 5 squared minus 4a and rc. All of this will be divided by 2a, and we will get a positive x value of 0.001365 molar. So this is our concentration of our hydroxides. So our concentration of our hydroxides was 0.001365 molar. The negative log of this value will give us our pOH. So the negative log of 0.001365 will give us a value of 2.86. And then our pH will equal 14 minus 2.86, which will give us a final value of 11.14. So the pH of our weak base in our flask is going to be 11.14. This makes sense because all we have is a weak base in our flask and no acid has been added yet. Alright, moving on. Let's look at our next question. What is the pH of the solution when 26.25 milliliters of 0.1 molar HCl has been added to the flask? The first thing to do is to calculate the moles of HCl being added. So, moles can be calculated by molarity multiplied by volume. 0.1 molar multiplied by 0.02625 liters is equal to 0.002625 moles HCl. So that's how many moles of HCl we're adding to our flask. And how many moles of ammonia is in our flask? Well, we know we had 0.105 molar, and we had 0.05 liters of it, and this will give us a value of 0.00525 moles of NH3. So the weak base is now going to react with the strong acid. We draw a rice table, we can look at this reaction. So our base is going to be reacting with our acid that's being added, and that's going to make our conjugate acid, which is ammonium. Our initial amount of NH3 would be 0.00525 moles. The initial amount of our protons would be 0.00265 moles. The reason we know the amount of moles of our proton is because a strong acid, which is HCl, it will fully dissociate, so we'll have the same amount of moles of H+ as we did HCl. And we have 0 of our conjugate acid. What is the change? Well, we'll be using up all of our free protons because the base will react with it, so all of that will be used up. We'll gain that on the other side. Okay, and what is our final equilibrium value? Well, we have 0.002625 moles of ammonia, or B, and our BH+, we would have 0.002625 moles of our BH+. So now we know our equilibrium values after we've added 26.25 milliliters of 0.1 molar HCl. The next step is to use the Henderson-Hasselbalch equation, because now we have a conjugate base and a conjugate acid pair existing in our solution. So pH is going to be equal to our pKa plus the log of our B, which is a deprotonated species, or BH+, which is a protonated species. So what is our B to pH+? Well, we just calculated our final equilibrium values, and we can use moles in this fraction instead of molarity because the unit moles will cancel out. So the log of 0.002625 over 0.002625 will be the log of 1, and that would be equal to 0. So our pH will actually be the pKa plus 0. And what's the pKa? Well, we were given our Kb, and that was 1.8 times 10 to the negative 5. And if we want to get our Ka, all we do is Kw divided by our Kb. That would be 1.0 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5, which will give us a final value of 5.56 times 10 to the negative 10. So our pH will equal the negative log of our Ka, because the negative log of the Ka would be our pKa. So the negative log of 5.56 times 10 to the negative 10 will give us a pH of 9.26. So what is the pH of the solution after adding 26.25 milliliters of HCl? It's going to be 9.26. And so you can see the pH started to drop slightly because a strong acid was added. It's also important to realize that before our equivalence point volume, we have a buffer solution. The reason we have a buffer solution is because all of our strong acid has been used up, and so we have our conjugate acid-base pair, which is ammonia and ammonium, existing in the solution. So that's why we have a buffer, and the pH will not drastically decrease when we're adding our strong acid. Another important thing to realize is that when our pH equals our pKa, that means we are at our 1/2 equivalence point volume. So whenever your pH equals the pKa, that means we're at 1/2 of the equivalence point volume of our strong acid added. So our next question is, what is the equivalence point volume and what is the pH at this point? Well, from our previous question, we calculated the 1/2 equivalence point, and that was 26.25 milliliters, which was given our question. So the equivalence point would simply just be 2 times 26.25 milliliters, which would give us 52.5 milliliters of HCl added. But what's another way of calculating this equivalence point volume? M1 V1 is equal to M2 V2, where M1 is the concentration of ammonia and V1 is the volume in our flask and M2 is the concentration of HCl. So if we do that, the concentration of ammonia was 0.105, the volume of the flask was 0.05 liters, and that was equal to a concentration of 0.1 molar HCl multiplied by V2. If we solve for V2, we're going to get a value of 52.5 milliliters. So that's another way of calculating our equivalence point volume. So our next question is, what is the pH at this point? So when we have added 52.5 milliliters of 0.1 molar HCl, what is the pH? The first thing to do is to calculate the moles of HCl we're adding. So 0.100 molar HCl multiplied by 0.0525 liters of HCl will give us a final mole amount of 0.00525 moles HCl that we're adding into our flask. And again, how many moles of ammonia is in our flask initially? Well, we have 0.105 molarity times the volume, which is 0.05 liters, and we get 0.00525 moles of ammonia. And we can see that this is our equivalence point because the moles of our ammonia and the moles of our strong acid HCl are the same. So let's do a rice table to calculate the equilibrium values after the reaction. Our base is going to react with our strong acid to create our conjugate acid. The initial amount of our base is 0.00525 moles, and the same is for our acid. And we have no conjugate acid right now. All of the base and the strong acid would react, and they would create our conjugate acid. So our equilibrium values is just 0.00525 moles of BH plus, which is our ammonium ion. The next thing to do is calculate the pH of our weak acid ammonium. But to calculate the pH, we need a molarity. We're given moles. So let's first calculate the molarity of our conjugate acid. So the molarity is simply our moles of our conjugate acid divided by the liters of the solution. So our solution initially had 0.05 liters, and we just added 0.0525 liters of HCl. So our new molarity would be 0.0512 molar of BH plus. And now we have to figure out what the pH of that weak acid is. So to figure out the pH of our weak acid, we have to do a rice table. So what is the reaction of our weak acid? Well, the weak acid is simply just going to dissociate into its conjugate base and a free proton. Our amount of our weak acid is 0.0512 molar. Again, now that there's only BH plus in the flask, we can consider that as a constant volume, and we can use molarity as our amounts. It will be dissociating, and we will be gaining B and H plus on the other side. And our final equilibrium values is 0.0512 minus X, X, and X. How do you calculate the pH? Well, you need the Ka expression, which is B times H plus all over our BH plus. And that will give us a value of 5.56 times 10 to the negative 10. What is our B? X. And what is our H plus? X. And our BH plus is 0.0512 minus X. So we have to solve for X. And what will X give us? The concentration of our protons. So we can find our pH from that. So there's two different ways of solving for X, the approximation method or the quadratic formula. Let's try using the approximation method. If we tried doing that, we would have X squared on top and our initial concentration is 0.0512 on the bottom, ignoring X in the denominator because we assume that's such a small value it does not affect our calculations. And we set that equal to our Ka, which we said was 5.56 times 10 to the negative 10. If we solve for X, we get X equal to 5.33 times 10 to the negative 6 molar. Let's quickly check if we can assume that this value is correct. Do that by plugging our X value that we just solved for and dividing it by our initial concentration and multiplying it by 100%. And if this is greater than 1%, we reject, and if it's less than 1%, we accept it. And since it gives us a value of 0.01%, we can accept this value, and we can assume that we can ignore the value of X in our denominator. So the negative log of our X will give us our pH, and the negative log of 5.33 times 10 to the negative 6 gives us a pH of 5.27. So at our equivalence point, we have a pH of 5.27. And does that make sense? Yes, because all of our weak base and our strong acid reacted, and all that we have left is our weak acid. So the pH of a weak acid should be lower than 7, and we have a relatively low pH, 5.27. All right, let's look at our last pH calculation. What is the pH after adding 60 milliliters of 0.1 molar HCl? Always, we have to first calculate how many moles of HCl is being added. So 0.100 molar multiplied by 0.060 liters will give us a mole amount of 0.006 moles HCl. And we know that in our flask, we initially have a mole amount of 0.00525 moles NH3. Let's do a rise table to see how they will react. And we know that we're going to be having excess HCl because we're past our equivalence point. So there should be excess strong acid in our solution. So the reaction will be a base reacting with our acid to create the conjugate acid, which is BH+. Our initial amount of our base, 0.00525 moles. Our initial amount of our acids, 0.006 moles. And we're assuming we have no BH+ yet. What is the change? Well, we're going to be losing all of our base to the acid. And we'll be gaining that as our weak acid. So there's no base left over, and we have an excess amount of our acid in our solution, and we have a small amount of our conjugate acid in our solution. So now that we're past our equivalence point, we have an excess amount of our strong acid, our protons. So we don't have to consider the effect of our weak acid on our pH. This value is insignificant in the presence of our strong acid, which is our free protons. So all we have to do is calculate the pH of the concentration of our protons. So to calculate the concentration of our protons, we first have to get a molarity. We know we have 7.5 times 10 to the negative 4 moles of our protons. But what is the volume? Well, the volume is 0.05 liters that was initially in the flask, and 0.06 liters that we just added to the flask. And that gives us a final concentration of 0.00682 molar. So that is the concentration of our protons. So the negative log of our H plus is going to give us our pH. And we calculate the concentration as 0.0682 molar, which gives us a final value of 2.17. So our pH after 60 milliliters of HCl has been added to the flask is 2.17. And this makes sense because now we have excess acid in our solution and there will be no base in our solution. And that means that the strong acid will have a really strong effect on our pH, and it'll be a really acidic pH. And our value is 2.17, which is a very low number, which means it's a very acidic pH. And we did not have to consider the effect of our weak acid in our solution in the presence of our excess strong acid. All right, let's look at the titration curve for a weak base with a strong acid. So we can see that we start out with a high pH because all that was in our flask was NH3, which we denoted as B because our base was the only thing in our flask. Slowly we started to add small amounts of our HCl. So our pH would slightly start to lower because we were adding protons into our solution. And this created our buffer. Our buffer region was where we had used up all of our strong acid and we had B and BH plus both in our solution. And so if you have a conjugate acid-base pair in your solution, you have a buffer. So you can see that the equivalence point volume is, say, 100 ml. And at the 1/2 equivalence point, our pH was equal to the pKa. And the reason it was equal to our pKa was because the amount of our B to BH plus was a 1-to-1 ratio. And that meant the log of that ratio equaled 0. So our pH was just left to our pKa. And at our equivalence point, you can see that the pH equals 5.3. And all of the strong acid had reacted with our base, leaving us with our weak acid. Past our equivalence point, you can see that the pH drastically decreases because now we have excess H plus in our solution, which is a very strong acid, the protons itself, and that drastically decreases the pH, and you can see the buffer no longer applies in this region because we have strong acid left in our flask and no base. So for all of these acid-base titration videos, you should definitely rewatch them to make sure that you have enough practice. There's a lot of concepts to go over and there's a lot of reactions that are going on. And so practicing over and over again, you'll get really good with these titration questions. So if you enjoyed the video, make sure to leave a comment, subscribe, drop a like, and have a good day.